In previous sections, it was mentioned that several of the quantities that we looked at were state functions. We're going to examine what it means to be a state function through the use of Hess's law. And let's just recall that a state function is a property of a system that only depends on the present state. It does not depend on the system's past or future. If we think about traveling between two cities, how long it takes to get to the destination depends on the path taken and the speed at which one travels. So the length of time it takes to get someplace is not a state function. It is dependent on other properties. But once you reach your destination city, the elevation that you are at in that destination city only matters on the city that you're in, not on how you got there, or the time of day, or the month, or anything else. It is an independent state. Well, in going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. So change in enthalpy is a state function. If we look at a chemical reaction as a reorganization of chemical bonds, there are certain bond energies associated with our starting reactants and other energies associated with our products. The change in enthalpy, or the heat of a reaction, is the difference in energy released upon bond formation in product compared to energy required to break bonds in starting materials. So the change in enthalpy for a chemical reaction is only dependent on the particular reaction that we're looking at. As an example, let's look at the formation of nitrogen dioxide. We can look at the formation of nitrogen dioxide from nitrogen gas and oxygen gas in one step, where our change in enthalpy is 68 kilojoules. We can also carry this reaction out in two distinct steps, where we take 1 mole of nitrogen and combine it with 1 mole of oxygen to give 2 moles of nitrogen monoxide. The change in enthalpy for that reaction is 180 kilojoules. And then a second step where our nitrogen monoxide combines with another equivalent of oxygen to give us nitrogen dioxide with a change in enthalpy of negative 112 kilojoules. If we sum these two reactions up, then we get nitrogen monoxide canceling, and overall we get nitrogen gas combining with two equivalents of oxygen to give 2 moles of nitrogen dioxide. We can add the change in enthalpies up. Change in enthalpy 2 plus change in enthalpy 3 is equal to 68 kilojoules, which is equal to change in enthalpy 1. So it doesn't matter if we go through one step or through two steps, the change in enthalpy in going from nitrogen and oxygen to nitrogen dioxide is 68 kilojoules. We can look at this another way. In the two-step reaction, we go from nitrogen and oxygen to oxygen and nitrogen monoxide. The change in enthalpy is 180 kilojoules in an endothermic process. And then In an exothermic process, we get our change in enthalpy 3 in going from oxygen and nitrogen monoxide to nitrogen dioxide. The change in energy between nitrogen gas and oxygen gas in going from nitrogen and oxygen to nitrogen dioxide is the same as in one step, where nitrogen dioxide is higher in energy by 68 kilojoules. So there are a few things that we can do with our enthalpy changes. If we reverse a reaction, the sign of our enthalpy change will also be reversed, and we'll see that the magnitude of our enthalpy change is directly proportional to the quantities of reactants and products in a reaction. If the coefficients in a balanced reaction are multiplied by an integer, the value of our change in enthalpy is also multiplied by that same integer, and we can sum up a series of reactions to get a reaction that we're interested in. So let's consider the following data. The change in enthalpy associated with the dissociation of ammonia gas into nitrogen gas and hydrogen gas is 46 kilojoules. The change in enthalpy associated with the formation of water from hydrogen gas and oxygen gas is negative 484 kilojoules. We can use these two reactions and their heats of reactions, or enthalpies, to calculate the change in enthalpy for the reaction between nitrogen gas and water to give oxygen gas and ammonia gas. When we want to use Hess's law in problem solving, it's a good idea to work backward from the required reaction and then examine the reactants and products that we have so that we can decide how to manipulate other given reactions in order to get the sum of what we're looking for in the reaction that we're interested in. We can reverse any reactions as needed to give required reactants and products, and we can multiply reactions to give the correct number of reactants and products. Keep in mind that if we reverse a reaction, then the change in enthalpy sign will reverse, and if we multiply a reaction, we multiply our change in enthalpy by that same value. So if we reverse the two reactions that we're presented with, then we have reversed enthalpies for the formation of ammonia and for the dissociation of water into hydrogen gas and oxygen gas. We now have something that is more closely resembling what we're interested in. We're interested in ammonia and oxygen as products, nitrogen and water as reactants. Now all we need to do is multiply the reactions to give the correct number of reactants and products. We can multiply our reaction for the formation of ammonia by 4, and the reaction for the dissociation of water by 3. We'll multiply our change in enthalpies by 4 and 3 respectively, which gives us, after canceling out hydrogen gas, a sum between our two reactions that resembles the desired reaction. If we then add our change in enthalpies, we get the change in enthalpy for the desired reaction of 1,268 kilojoules.